So we're going to continue with our statistical review. Just kind of like a summary of what we did the first class. We started with the general concept of population, sample, and then basically, as a reminder, what we usually do in statistics is to try to learn something about the population using just sample information. Okay, so that's the basic concept. And of course, the things that we want to know about the population are related with characteristics of that population, and the way that we measure those characteristics are using using variables. Okay, so once we have that information about the variables, we have what we call these statistics. We have the sample mean, the variance, the sample standard deviation, the histogram, etc., which are sample statistics. And since again we're always talking about the relationship between the sample and the population, so what we did in the previous class was to talk about the concept in the sample and what is the related concept in the population. Okay, so it was kind of like a review of those concepts that I'm sure that you've seen in the past. So today, we're going to be talking about this new topic, which is related with the sampling distributions and the central limit theorem. Which, again, this concept of sampling distributions is a concept that is kind of key to everything that we do in statistics. Okay, so I'm going to spend some time explaining you the intuition behind it. Okay, so once again, and I repeat this concept again and again, is that we use sample statistics. So for example, our sample mean, which we call it X bar, to make inference about the population. Okay. But so remember, you're going to take a sample for the mean. Okay? And remember, but the objective is to know something about the population. So usually, the natural question is, okay, so how close is this sample value to the true population value? Okay, or so how reliable is this sample statistic as a measure of the true population value? Because again, so remember, you have something that you obtain for the population, and you want to know something about it. Now, so to try to answer these questions, we use what is called the probability distribution of the sample statistics, which are also called sampling distributions. Okay, so again, to try to answer those questions of how close is the sample statistics to the population parameter, we use something that is called sampling distributions, which is nothing else but the probability distribution of the sample statistic. Okay? I know, so this is kind of like a higher level concept. Okay, so I'm going to try to go slowly so that you understand what's going on with this sampling distribution. Okay, so let's look at this example, and you will see how that works. So how do we obtain the sampling distribution of the sample mean? Just to start with, because sample mean in this case is our statistic of interest. So, as usual, let's start with a population of interest. And to make our life easy, let's think about that's the population of Texas Tech University students. These are TTU students. Now, the variable of interest is going to be a variable measuring the height of students, and we know that that population has a mean, with mean mu, and a standard deviation sigma. Okay, so that's the value that exists in the population and that we don't know. So of course, to know the mean, if you think about that, to know the mean of the population, what we could do is we try to get all of the students, go student by student at Texas Tech, and we have more than 30,000 students, and calculate the mean. So that would be the true population mean. Okay, so that's one way to get that value. So let's try to graph our 35,000 students. Okay, we can think that I mean, it looks like a petri dish, but those are supposed to be students. Okay. And I'll use later on like to take our samples. So again, so we, again, in an ideal world, we can go and collect this information for the 35,000 students, and then we can organize it. We could enter it in Excel, and then sort it, or organize it. It doesn't need to be sorted. So we have about 35,000 observations. Okay? So, you see, we have this variable. And of course, this variable is going to have a distribution. Everybody sees that. So see, for this population, for this variable has a distribution. So these values have a distribution. So that's the distribution of the original variable. The original variable. Okay, in this population. Oh, what did I do? Okay, so everybody's following this. I'm gonna make it smaller. So everybody follows that. So we have a variable, and the variable has a distribution. So that's the distribution of the original variable of interest, which in this case I call it height, and I guess I was using y, so I will be denoting it by y. Okay, so far so easy. I mean, that's the way that we tend to think about variables with distribution. But now what we're going to be talking about is the distribution of a sample statistic. So now let's see how that works. So remember here what we are talking about is the sampling distribution. Let me label it, of the sample mean. Okay, so let's think about the process of going and taking samples. We can go and walk through campus kind of like in a random way. So we can go and we can take a sample from these 35,000 students. And once we get that sample, let's say 100 students, we can calculate a mean. Everybody follows that. So we go to this population, take a sample of 100 individuals, and we can calculate a mean. So let's say we have a sample of 100 individuals. Oh, well, I mean, students, I guess. I'm not going to call them. Well, students are individuals too, but students. So, and I'm going to call it, and then we calculate the mean, which we can call it y bar S1 for sample 1. Everybody follows that? And of course, we can do this thing. We can go and take different samples. You see? So this was our first sample. So we can go the next day and take a different sample. And of course, we're going to get a different value for the mean. Everybody can see that? I mean, it's unlikely that those two values are going to be exactly the same. So we can go and do again this sampling exercise. So sample 1, let's number the sample. So then we can go and take sample 2 again of 100 students. And we will call it y bar S2. Another sample, sample 3. And then, of course, we can do these things a very large number of times. Sampling and resampling and resampling and resampling. So we say sample K, 100 students. And that will give us, so sample K. Everybody sees that. So now you see what we have. What we have is a series of values, of means. So now we have k different values of sample mean. And of course, you see these sample means also have a distribution. And that's what we call the sampling distribution. So you see the sampling distribution of the sample means is the probability distribution of the sampling means. Can you see that? So you see it's a distribution on the specific statistic, which is going to be different, again, than the distribution of the original value. Okay, so this is what's a sampling distribution. It's the probability distribution of any statistic, as a matter of fact. Here I'm using it as an example, the sample mean. But if you think about it, after we take our sample 1, we can calculate the sample mean, we could calculate the median, we could calculate the mode, we could calculate the standard deviation, we could calculate the variance, and actually we can end up with a sampling distribution for every sample statistics that you can think of. And those are called sampling distributions. Okay, so every time that you hear about sampling distribution, that refers to the distribution of the sample statistics. Okay, and again, and this is a concept that is kind of key to almost everything that we do in statistics. So here what we have once again, so we end up with y is 1, like the same way that we had, we could have organized these values in Excel after we take our samples. So we have k values for the sample mean. So in these results, in the probability distribution of the sample mean. The probability distribution, or sometimes you can call it sampling distribution. Of the sample mean. The sample mean. Okay, so that's kind of a big concept. And of course, so why do they call sampling distributions? Well, they are called sampling distributions because this probability distribution is originated due to the fact that it's originated due to sampling. Okay, so that's what's called sampling distribution. Okay, so any questions, guys? Okay, so, and from a broader perspective, and that's already kind of that I already had mentioned. Okay, even though here I gave you the example of the sampling distribution of the sample mean, from a broader perspective, actually we can have a sampling distribution for every statistic, for every sample statistic. Okay, so in general, and that's the way that usually things work. But of course, the mean is probably the most popular sample statistic that we use for our analysis. So, main idea is that all sample statistics for example, the sample mean, the sample variance, have sampling distributions. Okay. And of course, most of the time we're going to be making use of the sampling distribution of the sample mean, but the sampling distribution of the sample variance you have never heard of. But I think it's possible to do that. Okay. So any question, guys, about the sampling distribution? Okay. So key concept. Okay. So now let's move on. So far, I guess, I hope I have convinced you that the sample mean has a distribution. But now let's learn a little bit more about the characteristics of that sampling distribution for the sample mean. Okay? So let's talk more in detail. So in order for us to do that, we're going to be looking at some theorems about the sampling distribution of the sample mean. So let's again use y1, y2, and yn be a sample. So this is the original sample of size n from a population with mean mu and the standard deviation sigma. Kind of, similar to the example that I was using before. So we have a sample of size n from a distribution that has mean mu and the standard deviation sigma. And of course, the sample mean is going to be y bar. So let's y bar with the sample mean. So let's look at the first theorem. Again, there I'm not going to show you the proofs, but just we're going to discuss this. So the mean of the sampling distribution of y bar, which is, remember, that's what we're interested, is in fact mu. So you see the mean of the sampling distribution of y bar is mu. So the mean of the distribution of the sample mean is equal to the mean of the original distribution. I mean, that's what this thing is telling us. The mean of the distribution of the sample mean is equal to the mean of the distribution of the original bar. So, and the standard deviation of the sample distribution of, once again, y bar, the mean, which I guess, let me see, I'm going to be denoting it, denoted by sigma y bar is equal to sigma divided by the square root of n. Okay? Everybody follows that. Again, so remember, so let's go back to our example and then you will see. Okay, so let's go back to our example. So remember, here was the population of TTU students, and actually I was assuming that the mean was mu and the standard deviation was sigma. So we know that about the population. So remember, what we have right now, we have the sampling distribution for the mean. So what we're saying is that what we're talking about is the characteristics of the distribution of this sample mean. So what we're saying is, remember, here the mean of y was mu, and the standard deviation of y was sigma. Now what we have here is the mean of y bar s. Okay? So let's write it here. So this is, I'm going to remind you, this is for y, and this is for y. But now here, the mean for ys, we're saying that it's also equal to mu. So the mean for ys is also mu. So you see, all distributions, the original distribution and the distribution of the sample means have the same mean. So what about the standard deviation? The standard deviation for ys, which we call sigma ys, is going to be equal to sigma divided by the square root of n. So think about that for a second. We have these two distributions. So first of all, and let's try to graph it, okay? To see how do you think that's going to look like. Yeah, let me see. So let's look at a graph here. Before we get there, I don't know what happened here. Okay. Where do I grab them? Okay, I'll try to grab them. So let's say distribution of y versus the distribution of y bar s. Okay. So and they don't have to be normal, but let's assume that they are normal. I mean, when we was talking about the height, I never said that it was normal. Okay, it could be any other distribution, but let's make them look normal. So then we know that the mean is here, mu. So how this other distribution is going to look like? So again, so this is the distribution of the original population, given those characteristics. Okay, so it's going to be the same. That's a good question. You see it? Are you sure that's always going to be the same? I mean, there is only one case. Let me see how many. It's going to be one case. Let me think about it. In which case is going to be the same? No, it's never going to be the same. No. Yeah, sorry, I'm going to have to say no. So if you were to graph it there, to impose it on the other distribution, how's it going to look like?
If the sample size is large enough, it should be or approximate a normal distribution.
Okay, well, we haven't talked about the normal. Okay, so yeah, I mean, we will go down in a second. Okay. Okay. Well, yeah, let's go with the normality. But beyond the normality, I mean, how would you impose it there? So yeah, I'm going to take your assumption. Actually, in a second, I'm going to say that it's normal, but I haven't talked about that now. But yes, it's going to look like that too. But how? How does it look? How do we impose it? Here. I mean, is okay. So I'm going to give you some hints. The shape. Okay, let's assume that the shape is the same. Okay, that will allow us to move forward. Okay, so what about the location?
Can it be like narrower?
Okay.
Just because it's not as many cases in the population as in the sample.
The case is going to be narrower. Okay, I buy that one. But the reason, I don't know if I totally agree with it. Because look at what's going to be the variability. The variability of that distribution for the mean is going to be the variability of the original variable divided by the square root of n. So it's going to be smaller or larger? It's going to be smaller. Okay? Can you see that? It's going to be smaller. So usually the way that you're going to be looking at the other distribution, it's going to be look something like that. Of course, I mean, it's not exactly the scale. Because remember, the variability of the bigger one, I mean, remember that's given by sigma. And the variability of this one here is given by sigma divided by the square root of n. And usually your sample is going to be a little larger. Okay? Okay, of course, I haven't talked about the shape, which is kind of like the name. But here, I mean, I wanted you to be thinking about that. I mean, they are centered around the same value because the means are the same, but the variability is going to be different. Okay, so hopefully that helps you to think a little bit about what's going on. So remember, we're talking about the distribution of y bar. Okay, so we know that it has the same mean as the original distribution of the same mean as the mean of the original variable, and the standard deviation is going to be the standard deviation of the original variable divided by the square root of n. So that's what it's going to be. The variability is going to be small. Now, so this is where the next theorem comes. I mean, if you have large enough n, actually, the mean, sample mean is going to be normally distributed. Okay, and that's what Eduardo's your name? Yeah, that's what he was saying. And that's kind of what we were assuming. So and that's what actually, theorem 1 and 2 imply what's called the central limit theorem. So that's the famous central limit theorem. Which tell us that the sampling distribution of the mean, of the sample mean, is normal with mean mu and the standard deviation sigma divided by the square root of n. Now, so sometimes you will see, you're going to see this notation. You see this kind of tilde means follows, and you use this fancy n, or I don't know, and then you denote the parameters. Now, sometimes you can use the standard deviation, or you can use the variance. But for now, this is the variance. So again, this means like follows. It's short for follows. And this means normal distribution. And remember that the normal distribution is defined by two parameters, the mean and the standard deviation, or the variance. Okay, so everybody kind of follows. And and I already showed you the graph. Now, of course, something to be. And let me, I'm going to draw, and I've never done this thing. I think that's kind of. So remember, we looked the first example when we were assuming that y was also normal. That's kind of what we have. So remember, that's the graph that we had before. So example 1. So we say that it looks something like that. So that our distribution for, so this is the distribution for y, and this was the distribution for y bar, for the mean. Okay. Now, you see what is very powerful about this central limit theorem is that we do not, we're not assuming that the distribution of the original variable has to be normal. As a matter of fact, it can be non-normal, okay? And that's why it's so powerful, this result. Even if the distribution of the original variable is non-normal, the distribution of the mean of that non-normal variable is going to be normal. Okay, everybody's following that. So remember, that's what we have here. So initially in the example, when I was drawing it, I was assuming that the distribution, kind of the shape of the distribution of the original variable was normal. Okay? And of course, the distribution of the mean is also going to be normal. But what I'm saying is that nowhere in this result, okay, we were assuming that the distribution of the original variable was normal. Actually, it can be non-normal. So, for example, so you see that result, for that result to hold, you can have something that looks, so this is something that looks like a log normal distribution. You see like a very long tail. So let's say that this is the distribution, and I'm going to give it a different name, Z. You see, if we were to draw the distribution of the mean of Z, let me see, so this is the distribution. So the mean would be the mean, of course, of both distributions, and the standard deviation is going to be, once again, sigma divided by the square root of n. Is that clear? And I'm not trying to confuse you here. the main idea here is, according to this central limit theorem, the distribution of the mean of any variable, regardless of the distribution of the original variable, is always going to be normal. And the mean of that sampling distribution is going to be equal to the mean of the original variable, and the standard deviation is going to be equal to the standard deviation of the original variable divided by the square root of n. Okay? So the sampling distribution of the sample mean, another way to say, is that the sampling distribution of the sample mean is always normal. Okay? So regardless of the distribution of the original variable. I mean, that's kind of the point that I was trying to make. Because if you go up and those theorems and all the assumptions, we never were assuming that the original variable was normally distributed. But of course, for that, and again, so this result holds. Be careful for large n. So I know that every time students ask me, so how large does n need to be considered large? Well, I think that kind of the rule of thumb for this specific result is that n is higher or equal to 30. Okay. Oh, what happened? I don't know. Oh, let's see. Maybe this thing jump. Okay, yeah. I don't know, since last semester, I haven't problems with that. Okay? So any question, guys? Is that clear? Okay, so I mean, I know that some of you are going to be saying, oh, okay, this sounds great, but so what? So what do we do with this thing? Well, so what are the implications? And that's kind of what I call two things to remember, or kind of the implications. So let's look at the implications of that result that looks very theoretical. So and I'm going to divide the implications first for applications. So you will see that the sampling distributions are important. So it's important to know the sampling distributions. Because they can be used to make a statement about the true population values using the sample statistics. So, knowing this sampling distribution is what going to allow us to say something about the true population value. Now, more specifically, basically, the way we do this thing is by using test of hypothesis and confidence intervals. Because those two things allow us to say something about the true population value. So you see, for example, in the context of hypothesis tests, the null hypothesis is that the true population value is equal to a certain value. So once you know the sampling distribution, you can do the test of hypothesis. And that will allow us to reject or fail to reject your null hypothesis that the true population value is equal to a certain value. Or with a confidence interval too, which allows us to say how confident you are that the true population value is between the lower bound and the upper bound. Okay? So, knowledge about the sampling distribution is what allows us to make those statements regarding the true population values, and the way that we go about making those statements more specifically is using both test of hypothesis and confidence intervals. So this is using tests of hypothesis and confidence intervals. Okay, so implications of the sample distributions for applications, and also are important for, there are some theoretical reasons behind it. Okay. And in a specific context, I'm going to be talking about two things, but let's write it down. So sampling distributions provide information about the properties of the sample statistic. About the properties of a sample statistic. So, and let's see specifically for our mean, the sample distribution of our mean, what two properties we can talk about. The first one is this property. Remember, and that was given by one of the theorems. So what in words, what is this telling us? The expected value is the same as the what?
It's the same as the population mean.
Yeah, well, the expected value is equal to the population mean, but more intuitively, so that's correct. Is that the average? Okay, so remember, the average of the distribution of the sample mean is equal to the average of the distribution of the original variable. Okay? Now, this property is called unbiasedness property of an estimator. This is called the unbiasedness that tell us that estimator is unbiased. Okay, so let's talk a little bit more about it because I don't feel that. So this is so here what we're saying. Well, I'm going to reword this thing. So we're saying is that the sample mean is an unbiased estimator for the true population mean. Okay. See, the sample mean is an unbiased estimator of the true population mean. So in our context, what this is telling us is that the sample mean is an unbiased estimator of the true population mean. Okay, but I want you to be thinking a little bit more about it. So this is, it sounds like great. Everybody's excited? I might take you excitement out of you just in a second. Unfortunately. So remember, what this thing is telling you, so remember this idea about sampling distribution. So this is a property of sampling distribution. Okay, so another way to say this thing is if you go and take samples and calculate the mean again and again and again, the average of those means are going to be equal to the true population value. Did you follow me? So see, if you go and take these samples and calculate the mean again and again and again, the average of those means are going to be equal to the true population value. However, what's going to happen with the specific mean? Is the specific mean going to be equal to the true population value? So remember, like in the example that we had with 100 students. Remember, you go and take a sample, you calculate the mean. Is that mean going to be equal to the true population value? No. Actually, you can, it's very likely. Actually, if it's a continuous distribution, the probability that's exactly equal is 0. Okay? So that's the reality. So I know that this property sounds great, and this is good for tests, for statistics. It's a good property for statistics. Basically what this thing is telling you is that when you calculate the mean, you're only going to be correct on average. It's means that only on average is that the sample statistic is going to be equal to the true population value. But for a specific sample mean, for one sample, that is not going to be equal to the true population value. I mean, yes.
So is that saying that the average of the average?
Yes, the average of, that's another, I like it. So the average of the averages is equal to the true population value. But the specific average is not going to be equal to the true population value. Actually, I like it. I like that way to put it. It's probably simpler. Okay, so I mean, you can write it that way. So another way to say it is that the average of the averages, well, and actually it's of a very large number of averages since it's the expected value, is equal to true population mean. Okay? So that is reality. So that's sometimes that's what happens. I mean, you go and do an experiment, you find a value, but then you can go and do another experiment and you can find a different value. Okay, so now actually that's why nowadays we care about this meta-analysis. They're becoming very popular because you go and try to get a general idea of what all these people have been doing in these different experiments. Kind of the same idea. I mean, you are trying to get the average of the averages to see if you are finding something. Okay, so again, so it's very important this unbiased, and you can see that basically, the good thing is that the sample mean is an unbiased estimator of the mean, but that's good. I mean, I always say, and that's what also statisticians are not rich, because basically that also means that you are never going to be able to totally know the truth. They don't have money, so you cannot predict. They cannot predict accurately. I mean, they are only going to be correct on average. Okay? So that's the first property, which is called unbiasedness. So let's look at this other property. So remember, the property had to do with the sample mean being equal to, well, the sample standard deviation of the sample mean being equal to the standard deviation of the original variable divided by the square root of n. Now this property is called consistency of an estimator. Okay, so this is called consistency of an estimator. And another way to think about this thing is to remember. So we're saying that the sample mean has a distribution. But you see the variability of this distribution gets smaller and smaller and smaller as the sample size increases. Okay, so the consistency property basically is telling you is that the distribution of the estimator gets concentrated around the true population value as your sample size increases to infinity. Okay, so you see for a sample that is of size infinity, the variance is actually 0. Okay? So basically the distribution has to be located exactly on the mean value. That's what this thing is telling you. So it's called consistency since the distribution y gets concentrated around mu as n goes to infinity. Okay, so and I'm running out of space here. So I'm gonna open a new page and so that you can see graphically what that means. So you see, if we were to again, draw the distribution for y, So let's say it would be the distribution for y, but when the sample size is only 100, you see this thing will get smaller and smaller. So let's say this should be for y with 1,000. And of course that thing is going to get even, and of course it has to be larger, much larger, but I ran out of space because that area is supposed to add to 1. Byn is equal, let's say, to 10,000. Okay? And of course, I could go the same thing in the same graph. I should be drawing the same thing in the same graph, but that's the idea. Okay? I wanted to show there's how the variance gets smaller and smaller and smaller as your sample size increases. So it gets concentrated. So with n is infinity, actually this thing is 0. And you just hit exactly the mean. But of course, that never happens. But that's kind of the general idea of why. Remember, we prefer larger sample sizes to smaller sample sizes even to calculate the mean, because you are more likely, having a large sample size makes you more likely to be closer to the true population value for the mean. So that's one way to think about intuitively that. Okay, so those two kind of, again, so these sampling distributions are important because they allow us to get information about the properties of our estimator, our sample mean. Okay, so kind of a bit more theory. So now let's look specifically at an application, and you will see how it actually works. So let's look application of the central limit theorem. So as I was telling you, we can use this for tests of hypotheses, or also for confidence intervals about mu. Okay. And I'll use the confidence interval about mu only. Okay, and later on, and again, so to give you a general sense of what I'm doing, again, so this is kind of like a review. So I'm also trying to remind you how you go about calculating confidence intervals, test of hypotheses, while at the same time, we introduce these new concepts. Okay, so now let's focus only on the confidence interval about mu. So the confidence interval for mu with a large sample, so remember this is n higher or equal to 30. So let's calculate a 1 minus alpha confidence interval. So remember, so what's alpha? How do we call this alpha usually? It's what you see in the level of significance. It's the level of significance for tests of hypotheses. Okay, so let's learn to do this thing. Well, so given the fact that we know that our sample mean is normally distributed with mean mu and standard deviation sigma over square root of n, actually we can come up with a formula for the confidence interval. Okay, so you see this formula for the confidence interval, another way to say it, the formula for the confidence interval I'm going to give you uses the fact that the sampling distribution of the sample mean is normally distributed with mean mu and standard deviation sigma over the square root of n. Okay, so again, the formula for this confidence interval is derived using this information about the sampling distribution for the sample mean. So given that the sample mean follows a normal distribution with mean mu and standard deviation sigma over square root of n, then the 1 minus alpha percent confidence interval for mu is given by one minus alpha 100% confidence interval for mu is equal, so it's gonna be y bar minus z alpha over 2 s divided by the square root of n y plus c alpha over 2 s divided by the square root of n. Okay, and I'm gonna define everything, single element of this. Okay, but the bottom line here is that this formula for the confidence interval is based on the normality of the sampling distribution of our sample mix. Without that, then this formula wouldn't be valid. Okay? Because if you think about it, so for example, if you think about it, this formula kind of is, it's kind of it's symmetric. You see, what you think that it's to the left is also to the right. And again, and that's because we know that it's normally distributed. You see, if it was not normally distributed, then the formula for the confidence interval, probably is going to be something else. It should be different. Okay. So now let's look at each of the elements of the formula, and then we will have an example. So Z is the standard normal distribution. So what's the mean and the standard deviation of the standard normal distribution? So the mean is 0 and the standard deviation is 1. So remember, y is just the sample mean. S is the sample standard deviation. Okay. Now let's see specifically what that Z alpha over 2 value is. So that Z alpha over 2 is the value of Z that has an alpha over 2 probability to its right. I know that sounds complex, but I'll do a graph. In a second I'm going to show you a graph and you will see that it's quite simple. And probably you remember from your basic stats class. You have this Z, you have these tables for the Z distribution, for the T distribution. So part of the objective here is to remind you how that you use those tables. Okay? So we start with the Z distribution. So Z is just a variable. Remember, if we were to graph that Z distribution, it looks like that. So of course the mean is normal. So it's going to be symmetric, bell shape, mean 0, and the standard deviation is going to be 1. So in the formula we have this Z alpha over 2 value. So I was telling you this Z alpha over 2 value is a value of Z. So here is a specific value of Z. Remember, here we have this is f of Z, and these are specific values of Z. So this is going to be a specific value of Z that has a probability to its right of alpha over 2. Okay, so the probability to the right z is going to be alpha over 2. So the probability that any value of z is higher than z alpha over 2 is equal to alpha over 2. And z means any value. Everybody understand that? Okay, so that's what is z alpha over 2. Okay, so and this is where things get kind of complicated. So different books have different tables, and the tables give you this information in a different way. So the one that I pick is one that I believe is easier than the one that we have in our textbook. So I already gave you the handout. Okay? Because remember, so big picture, before you get lost into the details, what we're trying to do is we're trying to calculate these confidence intervals. Okay? So we already know what's the mean, we already know, well, I haven't defined S, but I record root of n, and we're trying to find out how we find the z alpha over 2. Okay? So we're saying that this is a value from the z distribution. So how do we find that value? Well, it depends sometimes on the type of table that we need. But first, in terms of definition, this c alpha over 2 value is that value of z that has a probability to the right of alpha over 2. Okay? So the question is, how do we find that in the table that I just gave to you? Okay, which is this one. So this is standard normal probabilities. So you see to the left, you have the value of z. Well, it's to the left column, and also, on the top. So these two gives you the value of z. And what you have inside are probabilities. Okay? So, for example, minus 3.40. Well, okay, I'll give you in a second. Okay? And what is inside probabilities. Okay? So for now, everybody, so we have this table. Okay, so now let's go back to what we're trying to do. So, so we know what that C alpha over 2 is, but the question is, how do we get that C alpha over 2 from that table that I just gave? Okay, so how to get, so now we know what is that, but we don't know how to get it from that table. C alpha over 2 from the table. Okay, so to figure that out, so first notice that what the table gives us is not the probability to the right, but the probability to the left. That the table gives us the probability to the left of C alpha. The probability to the left, so that if we were to graph this thing, again using our C alpha over 2 value that we are looking for, you see what you have inside the values of that table are these probabilities to the left. Okay? So so what we have there is the probability that z is less than z alpha over 2, which is equal to 1 minus alpha over 2. Okay? So I guess it's kind of tricky. But in a second you are going to see that's actually very easy to do this thing. So thus, this is what we need to do. Using this table, we find C alpha over 2 as follows. So first we need to calculate 1 minus alpha over 2. Okay, so usually remember, we're given the alpha, and then what we have to calculate is 1 minus alpha over 2. So that's the value of the probability. So that's a pro. Well, I don't want that. Let me see how I close this thing. Okay. So this is a probability. In the second step, what we do is we look for z value in the table that corresponds to 1 minus alpha over 2. And that's the z alpha over 2 value. Is the z alpha over 2 value. Okay? Okay, so let's look at an example, and you will see that probably it sounds complicated. Maybe I made it sound more complicated than it is, but see. I need to add some pages. I ran out of pages. And I always forget. Oh, okay, a pen. I choose a pen. It's at the end. If you do insert it. But yeah, thank you. Yeah, that's exactly what I needed. Okay, that's all. Thank you. Okay, so let's look at an example. So let's say that the alpha that you are giving is 0.10. Of course, first we need to calculate alpha over 2, which is 0.05. And then we need to calculate 1 minus alpha over 2, which is equal to 0.95. So this is the probability. And with that probability, we can identify the z value that correspond to this probability. So the z alpha over 2 value for 0.10 over 2, which is 0.05, is going to be equal to, so can anybody help me? So again, the probabilities are inside, so we have to be looking for is that 0.95. So look for the p-value inside the table. So 1.6, okay, so you say 1.6, and then? So this is 1.6, so what Anna is saying is somewhere around here. Is it 1.6? So we're looking for 0.95. Of course, we didn't find the exact value. Okay, so we know that it's somewhere here, which means that it corresponds to a value of z that is between 1.64 and 1.65. To make our life easier, we're going to assume that it's exactly in the middle. So we're going to say that's 1.645. Can you see that? So that z, so you see, I was telling you that the value of z is given to the left and to the top. And the probability is inside. So with that, we say that this is 1.645. Okay, so this is our z alpha over 2 when alpha is equal to 0.10. Okay, so for you to practice, I'll give you 1 minute. So what is if alpha is 0.05? Okay, and I'll help you with the calculations. But then, hopefully you are looking at that value on the table. So what's that value? So again, you have to go and look in the table for 0.975. Everybody got that one? Again, you go to the table. We're looking for 0.97. 0.975. Actually, in this case, we found the exact value. We respond to a Z of 1.96. Okay, so that's kind of usually the rule of thumb for a 5%, for a 95% confidence interval is about 2. I mean, if you ever forget, that's what, we use that 1.96 value. So which then that's equal to 0.196. Everybody follow that? So, very straightforward. I mean, it's kind of tricky to get to remember how to use that table. But once you get it, it's very easy. Okay. So, the last thing that I guess I never defined when I was looking at that formula. So we know the sample mean for y. Now we know how to find that z value. That's from that table. So, and again, notice that z corresponds to a normal distribution with mean 0. And again, that's due to the fact that the sample distribution or the sample mean is normal. So that's why we use this z normal distribution. So, S, and I talked about that. So yeah, I talked about that in the past, but I mean, I had not defined it in the context again. So this is going to be the sample standard deviation, okay, which is different than the population standard deviation. So divided by n. So S is the sample. Oh, I already defined it. I didn't remember that. It's already back there. Okay, so let's look at an example with actual numbers. So this is an example from the book, and they have this data on parents' attention time for a sample of 50 twins. So n is equal to 50. So in hours per week. Okay. So why did some of you might be wondering, why did you pick that example? Well, I have twins. So I thought it was kind of a very interesting example. And actually, so these investigators were investigating something that they call, and I was even more interested after reading this, the way that they call this problem. It's called benign parental neglect. Which basically, you are not paying enough attention to your kids because you don't have time. Okay, so that's kind of the issue that they were analyzing. You have to divide your time between two kids. So usually, if you only have one kid, and you are able to spend more time with one kid. And if you have two, you have to basically split that time, because the amount of time that we as individuals have per week is kind of constant. So unless you hire some help from outside, the only thing that you can do is just divide your attention. Okay, so they have this data there, so I thought it was kind of interesting. Again, the average value, and I was telling you that sometimes I use X, sometimes I use Y, but it's just a matter of notation. The amount of time per kid was 20.85 hours. The standard deviation was 13.41 hours. Well, I was even more interested, and every time that you do analysis, you always should calculate the sample statistics. The minimum was 0.80 hours, which I thought was very little, and the maximum was very high, 48.20 hours. Okay, just out of curiosity, so that they also see how much time does it take care of kids. On average, 20 hours per week, that's a lot. Okay, so let's calculate at a 90% confidence interval. So if it's a 90% confidence interval, so calculate 95% confidence interval for the mean, okay, for the true population. So remember, we only have a sample. So we want to know the true population value of the mean of time spent, taking care of twins. So since we want a 95% confidence interval, what's the value of alpha? 0.1. And we know that it's just, we have to apply the formula. So 1 minus alpha, 100% confidence interval. I'm just rewriting the formula here. Z alpha over 2. In our case, it's a 90% confidence interval, which is going to be equal to 20.85 plus minus 1341 divided by the square root of 50. And we already calculated Z alpha over 2. So remember, that was the Z for 0.05, since alpha is 0.10. So remember, our Z over 2, that was equal to Z 0.05, and that's what we did previously. It was 1.645. So this confidence interval gives us 17.17 to 23.97. Okay, it's very straightforward. Give you like 30 seconds to take notes, and then we interpret. Remember, interpretation basically is to say that we're 90% confident that the true value of the average time spent taking care of twins is between 17.17 and 23.97. So we are 90% confident that the true mean is contained in this interval. Okay, so I don't want to talk details, but so remember, I was telling you that this information about the sampling distribution allow us to say something about the reliability of our results. So remember, when you go and look at this confidence interval, if the confidence interval is small, that really gives you confidence that you are close to the true population value. So like in this case, does that give you a lot of confidence that, it seems to be that you are close to something. Because sometimes you can come up with confidence interval that goes from 0 to a very large value, so you are not very confident. And that's kind of what I was talking about in terms of reliability. Kind of like a subjective type of assessment. But when you see these values, actually, I guess, if I see, it seems that they're close enough. Okay? So any question? So I have 2 minutes. So, of course, and I'm going to do this very fast, and you can practice at home. If we were to calculate a 95% confidence interval. So remember, we already did these things. So C alpha over 2 was 1.96. So that the 95% confidence interval will be 20.85 plus minus 1.96, and the same numbers for the standard deviation and the sample size, and that gives you 17.13 to 24.57, which, it's larger. Yeah, it's slightly larger, but still, I mean, it's not that wide for purposes of this problem. Okay. So, at the end of the day, today basically we talk about only sampling distributions and focusing on the sampling distribution of the mean. Hopefully, I mean, you got a sense of where does that come from. And the idea is that you have the sampling distribution because you can take different samples and come up with a distribution of the means. Okay, and those sampling distributions have characteristics. In the context of the sampling distribution for the mean, if you have at least 30 observations or more, regardless of the distribution, of the original distribution, the sampling distribution of the mean is always going to be normal. And we talk about why that is important. Well, I mean, it has some theoretical implications of what are the characteristics of the estimator, that also has implications for application. Because once we know that allows us to set up and to write the formulas, for example, for confidence intervals, and also for test of hypothesis. Okay, so that was kind of more or less the story of today's class. And I guess next week, so we don't have class on Monday. So I'll see you next Wednesday. We will start with regression, which is chapter 2. Okay, so starting next week, we'll start with chapter 2, and then chapter 2 is very short. So we'll start chapter 2 and chapter 3 almost very fast. Okay, guys, so have a good weekend.